In this video, we are going to discuss the Lagrange's theorem in group theory. The statement of the theorem is given here. Let G be a finite group and H be a subgroup of G. G be a finite group and H be a subgroup of G. Then the order of H. Order of H is the number of elements in H. It divides the number of elements in G, or the order of G. Then order of H divides order of G. The number of distinct elements of the right cosets is given by C, and also the number of distinct left or right coset. See, either left coset or right coset. You know that number of left cosets equal to number of right cosets. The number of distinct left cosets is given by the quantity order of G divided by order of H. How can we prove this? So let us consider all distinct left cosets of H in G. So we are going to we prove this result either fixing the left cosets or using the right cosets. So, okay, here we consider the left cosets. Only the left cosets we consider, and then we write all the left cosets. Okay. A1H, A2H. Let A1H, A2H, A3H, etc. to ARH be the left cosets. Then G can be, then the group G can be written as the union of the left of these left cosets, the union of all these distinct left cosets. You know that when two left cosets are taken, if either all of them, all elements are same. That means if one element of a left, when we consider two left cosets, see, we can say important property of left coset. That if one element of the left coset, see for example these two left cosets A1H and A2H we are considering. So suppose one element is present in the second, one element in the left coset is present in the second left coset. That means here one element of suppose X is an element of A1H and X is an element of A2H. Then all elements of A1H will belong to A2H and vice versa. And that means either the left cosets, two left cosets are completely same, or none of them are. None of the elements, element of the left coset, one left coset is present in the other left coset. That can be clearly stated that they are disjoint. So any two left cosets are disjoint. So we can say that either the two left cosets, any two left cosets are same, or the two left cosets are completely disjoint. And in that sense, using that property, we can write that G is equal to union of all these left cosets. So G is equal to A1H union A2H union etc. Union of ARH. It's because if there is an element in G, some X is an element of G. Suppose X is an element of G, then that X must be present in the left coset XH. So there will be a left coset which contains that element X. So every element of G is present in at least one, in one left coset. Okay, and then looking the situation in that way, then you can see that you can write G equal to A1 and G. You can write G as the union of the distinct left cosets A1H, A2H, A1H union, A2H union, etc. union ARH. And also we know that the left cosets, you take any two left cosets, their cardinality, that means number of elements in that left cosets, all are same. Okay, therefore cardinality of AIH equal to cardinality of H itself. Okay, and then considering all these facts, so we can say that we can write that cardinality, therefore the cardinality of G, we can write a statement, a relation connecting, we can connecting cardinality of H and cardinality of G. So because see G, when we take the cardinality of G, we can write that it's equal to cardinality of the first left coset plus cardinality of the second left coset plus etc., and the cardinality of the last left coset, that is cardinality of A1H plus cardinality of A2H. Uh, but each left coset is same as the cardinality of H, and therefore this will be the quantity here you are going to get on the right side will be some multiple of H, a multiple of cardinality of H. It will be a multiple of cardinality of H. The number that multiple cardinality of H is the number of total number of left cosets. So here the total number of left cosets equal to R. You can say that by counting the left cosets, you can say that it is it's R, 1, 2, 3, etc. So R left cosets are there. So we get the relation that cardinality of G is equal to, or order of G equal to R into order of H. Therefore, R equal to order of G by order of H, where what is R? R is the total number of left cosets. Okay, thus we have completed that, the proof of the result. We have a set of corollaries that can be proved using the Lagrange's theorem, the previously established theorem. First corollary, order of A divides order of G. See, it states that order of A divides order of G. So let A is an element of G. Let A an element of G, then order of A divides order of G. Let H is equal to let us consider a group H equal to the cyclic group generated by A. Let H be the cyclic group generated by A. Then it will be a subgroup. Then H will be a subgroup of G. See, because A is a member of G, A is a member of G, and the cyclic group generated by A will be completely contained in G. So H is a subgroup of G. Then using the previous result and also the fact that will be equal to order of the cyclic group generated by A, that will be equal to the order of A, that is order of A. Okay, and therefore order of A divides order of G. Thus we have completed that proof. Next, corollary 2. Groups of prime order are cyclic. Always groups of prime order are cyclic. As a proof, let G be a let us take a group. Let G be a group. It's of prime order. Let G be a group of prime order. And also let H be a subgroup of G. See, G, we take a group of prime order. That means its order is prime number. Also let H be a subgroup of, we assume that H is a subgroup of G. And since order of G is of prime order, then H must be the group H must contain only one element, that is the identity element. Why? Because if H is a subgroup, if H is not a if H is a proper subgroup of G, suppose that H is a proper subgroup of G, then it will have some order that is greater than 1. Order of H will be then greater than 1. But what happens then? And then using the previous theorem, using the Lagrange's theorem, the order of H must divide order of G. But you know that G has prime order. That means suppose P is the order of G, then P has only 2 divisors. First divisor is 1 and the other divisor is, second divisor is P. So 1 and P are the only divisors of the number P, which is a prime number. In that sense, and we can then say that if H is a subgroup of G, then H must be either equal to G, H must be either equal to G, or H must contain only one element, and that element, any group which contains a single element will be the set which contains the identity element. So that is the singleton element, a singleton group which contains the identity element only. So we get that result. Next, corollary 3. Corollary 3 states that a raised to order of g equal to e. That means when a is raised to the power of g, then we get the identity element a to the power of g equal to e. But we know by the corollary 1. We know by corollary 1 that that order of g equal to order of a into, by the corollary 1, by using corollary 1 we know that order of g equal to order of a into k. It's because the cyclic group generated by a, we can think about the cyclic group generated by a, it's a subgroup of g, and therefore using the corollary and the previous and the Lagrange's theorem, we can write that order of g equal to order of a into some integer number, some suitable integer. Okay, and therefore using that order of g as power of a, then a raised to order of g equal to a raised to order of a into k uh, equal to a raised to order of a in the whole raised to k. But a raised to order of a can give us the identity element e. Thus we get that here e raised to k, equal to e itself. Next, corollary 4. For every integer a and every prime number p, for every integer a and every prime number p, a raised to p mod p. A raised to p mod p means, a raised to p mod p equal to a mod p. That means when a raised to p is divided by p, we get a remainder. The same remainder we get when a is divided by p. So a raised to p mod p equal to a mod p. Or you can write that a raised to p is congruent to a mod p. If you know the meaning of that congruence relation, then you can write it in this way also. A raised to p is congruent to a mod p. How can we prove this? See, using to write the proof, we begin with this statement using the division algorithm. So we want the use of division algorithm here. Using the division algorithm, we can write that a is equal to pm plus r, where 0 less than r less than n less than p, r less than p. That means we are dividing the number a by p. We divide the number a by p, and the remainder is taken. The remainder is r. Remainder is noted, and we then we can write it as a statement like this: a equal to pm plus r, where 0 less than or equal to r less than p. And then we raise the value of a to the power of p. So a raised to a to the power of p then will become pm plus r the whole raised to p pm plus r raised to p. And when it is expanded using binomial expansion theorem, so using binomial expansion of this, we can write that we get uh, a set of terms. So a set of terms we get plus the last term, one term, that last term is r to the power of p. But the first all the first terms except the last term, so all the terms except the last term, see, all the terms except the last term in this expansion, when it is expanded using binomial expansion theorem, we can see that all those terms contains p. So you can write that it has a big into p. That means it's a number, it's a suitable integer, into p. That means all the terms except the last term is a multiple of p. So mp plus r to the power of p. So to prove that from this, it is clear that now to prove that a raised to p when divided by p when divided by p gives r as the remainder, it is enough to show that r raised to p when divided by when r raised r to the power of p when divided by p gives us the remainder r. So okay, why? Because of this relation, because of this expression and its expansion. Okay, so we will show that, we proceed to show that r raised to p, r to the power of p when divided by p gives us r, gives us the remainder r. So if r equal to 0, we now we need to consider two situations. When r equal to 0, if r equal to 0, it trivially holds. When r equal to 0, trivially holds this situation, because say when r equal to 0, then when r equal to 0, this quantity will be then 0. Here also we have 0, so a raised to b, okay, a raised to b, then when divided by here, what happens, a raised to b is then a multiple of b. A raised to b is a multiple of b, and therefore r raised to b, r raised to p also will be a 0, because it is 0. Since it is 0, r raised to p is 0, then it really holds. When r raised to p 0 is divided by p, what is the remainder? Remainder will be 0. So r will be 0. The remainder will be then 0. So in that case, it's a trivial situation. So we assume that r is an element of up, u of p, and so r. Why? Because r equal to 0 situation is that first case is now excluded. So after excluding that value of r equal to 0, then we can see that from this relation. So since from this range of variation of r, using the range of variation of r, 0 less than or equal to r less than p, so that 0 is r equal to 0 situation is excluded. So we get that r is a number which is one of the which is a member of this set 1 2 3 etc to p minus 1. See, r is one among this number, one number, these number is 1 to p minus 1, 1 2 3 to p minus 1. That means r is an element of u of p. Then u of p is a group of, but we know that u of p is a group under multiplication, under multiplication mode p. So by corollary 3, here we want to apply, we need to apply the corollary 3 by using corollary 3, r to the power of u of p, because the order of u of p. See, u of p acts as a group, then and also r is a member of u of p, and that is stated here. We know from here it is clear that r is a member of u of p. So r to the power of order of u of p, yeah, r to the power of order of u of p, when r is raised to the power of u of p, we get that e is the identity element of the group or up, but the identity element is very clearly 1. It is 1. So equal to 1 is equal to r to the power of that is equal to r to the power of p minus 1, r to the power of p minus 1. Okay, therefore see, when r is raised to the power of p minus 1, we get 1. That means r to the power of p minus 1 equal to 1 mod of p, and therefore r to the power of p, by multiplying both sides by p of this statement, the second last statement, we get that r to the power of p is congruent to, actually it's congruent to r mod of p. So r to, see, yeah, multiplying both sides by both sides of this expression by r, not by p. See, p is used to divide that. Okay, so multiplying both sides by r, then r raised to p is congruent to r mod p. That means when r raised to p is divided by p, and when r is divided by p, we get the same remainders. Okay, that's the end of the corollaries. Okay, thank you for watching.